It's Mr. Herringer again, and this is the chapter of 7.4, the shortest network connecting 3 points. As you reflect back on what we've talked about in this unit, remember our goal is to find the minimal spanning tree. We take a regular graph that may not be a tree that has weighted edges, and we figure out which tree we can pull from that graph in order to make a minimal spanning tree. Minimal spanning tree, of course, is one method of finding an optimal and efficient path or network. What we're going to be talking about in the next couple of chapters is the idea if you can actually leave your graph. If you drew a model, if you could actually leave the model. So let's go ahead and describe it. I mean, I know it's a tough thing to visualize, so hopefully as we move forward, you kind of get an idea of what I've been talking about. So this is our example. We've got these 3 cities out in the desert, and we know it's a desert because here, whoopsie, this looks like a, I don't know, either a kangaroo or maybe an armadillo. I don't know. And of course we have a cowboy and we have all this desert. So we've got open area. The distance between the cities are 500 miles each. When we model it, we get figure B. We're laying fiber optic cable, and if you were to guess that fiber optic cable is very expensive, you would be correct. So we need to make sure that we connect these cities with the fiber optic cable the cheapest way possible. And again, this is a network, which means that if I were to connect Alsea Springs to Booker Creek, and then in other words, if I were to do this, that's okay for a network. I could get from A to C just by going through B. So we're trying to create something like a minimal spanning tree. We want to create a tree that gives us the cheapest. As you can imagine, digging a hole and laying this cable is pretty expensive. So cheapest is going to be the shortest, because like I said, if you had to dig a hole for 500 miles, imagine all the people and the equipment that would take. Imagine the cable that has to go in the hole. It could take quite a bit of money. So we're trying to find, in this case, we're trying to find a network that's short as possible. So if we were to draw the minimal spanning tree, we could easily come to the conclusion of graph A here. It could be a V. We could have easily connected BC, CA. Doesn't really matter. Network or computer signals are fast enough to where as long as you have a live link, then everything will be fine. So we found the minimal spanning tree. If you added this up, the amount of miles it's 1,000, right? 500 for one link, that's 1,000. 500 for one distance and 500 for the other. So again, it's 2 sides because it's a triangle, and we found that our length is 1,000 miles. But now, imagine if we can come off of our graph. Like I was saying, up until this point, we've been kind of stuck to our wireframe. But let's imagine that we can come off. Look at figure B here. What we have done is we have taken the CA line and we have moved it to the midpoint of BA. So J is the midpoint of BA. We still have the distance from B to A, but the distance from C to A is actually shorter. If you remember discussing triangles in your past math classes, you know that the height of a triangle is typically a lot smaller than the length of one of the edges here. And indeed it is. It's 433 miles. So now we've found a cheaper way than figure A in order to lay this cable. And again, remember, we are leaving the graph. So if you add that up, we're now sitting at 933. miles. So that's better. But now, since we're leaving the graph, why don't we just go crazy with it? What if we take the J here and we slide it in that way? Whoops. We slide it in that way. What we come up with is this S. So this S point represents the center point between all of the cities. And if we connect the cities to the center point, notice that the number is a lot smaller per link, 288.68 miles. So if that's 288.68, this is 288.68, this is 288.68, you would get approximately 866 miles. So C, because we can leave the graph, C represents really the cheapest, most optimal tree that we can create. And, I guess I should point out too, this particular angles right here, all three of them equal 120. Remember from your geometry lessons that a circle is how many degrees? It's 360 degrees. These are a circle, but they're three angles in the circle, so therefore 360 divided by 3 is 120. So each one of the angles equal, let me kind of clean this up a little bit here. Each one of these angles equals 120 degrees. So it's what we call a perfect Y. Now let's quickly look at just a note about J and S that we created. These are considered junction points. They're not nodes because they weren't part of our original graph. We wanted to, I take that back. They are, A, B, and C are junction points, but we created J and S. They're new junction points. Basically, the definition of a junction point is where two or more segments of the network come together. So A has 3 junction points. Table B actually has 4 junction points because we included J. And then C has 4 junction points, A, B, C, and S. So we need to take a look at the types of junction points here. The native junction points are those that existed on the graph prior to us moving from the graph. So in our example, A, B, and C are our native junction points. Anything that we have to create outside of A, B, and C is considered an interior junction point. Something that's like J is an interior junction point because it's not a native junction point. And one more quick identifier. Remember in our example we had an S. We created the S point, which was the centerpiece or center point of that triangle. That is called a Steiner point. Now, a Steiner point is a perfect Y. It exists, basically all the angles in this Y are exactly the same degree. It's 120 degrees. So you get basically, you get this figure here. Okay, what I'm telling you, the main thing that you need to get from this chapter is that there are, at this point, 2 different ways that we can find an optimal network. We can go the minimal spanning tree, which is, if you have to stay on the graph, and then there's this Steiner point. The Steiner point represents the absolute quickest, most optimal way to connect points, not just using the graph. Now, there's a few rules. We can guarantee that statement is true. All right. So the Steiner point represents the most optimal when you're trying to connect 3 points. But there is a time that will not work. Because the Steiner point exists on 3 equal degrees, or 3 equal angles, all of which are 120 degrees, if your triangle has a obtuse angle, meaning that it's greater than the 90 degrees, then the angle, which I guess this one is the example, in figure A in figure A is the obtuse angle. It causes the center point of the triangle to actually be a little off. The distances, like if you were to find a center point of A, that's figure A, then it probably would be somewhere here. Whoopsie, I did it again. Somewhere here. But the distances, as you can see, between C and the center point, B and the center point, and A and the center point are not equal. So if you have an angle that is bigger than, is obtuse, or bigger than the 120, it actually trumps the Steiner point. So in that case, a minimal spanning tree would actually be cheaper than a Steiner point. So if you look at B, again, this triangle, the center point between the three, I'm looking at figure B, the center point of the Steiner point, or excuse me, the center point is the Steiner point, and it represents the most optimal method in this particular example. So let's take a second and find out why or how exactly you create a Steiner point. Now, keep in mind that this is not something that I'm going to ask for you to do, but I thought it was interesting, so let's go ahead and talk about it. So we've got figure A. A is the triangle that we're trying to figure out where the Steiner point is. If you go ahead and drop a triangle, an equilateral triangle, from any of the three sides. So we're looking at figure B here. Once we do that, we know that we can create a circle that circumscribes it. That's figure C. So now we've created this circle, and we need to connect A to X with a line, and where that line crosses the circle is the Steiner point. Isn't that fun? Aren't you glad I'm not making you remember this? So now that you know that, this is the end of the chapter.